Hi, in this session we're going to be talking about C++ Class Designer's Checklist. This represents an accumulation of a number of rules that I've gathered over a long period of time, representing both lessons that I think I've learned in my own programming and also a fair number of things that I've gleaned from the C++ programming community at large through sources such as the C++ Frequently Asked Questions list and a number of different books. What this list consists of is a number of things that a total of, 12 rules that I rather hope that all of you will consider whenever you're in the situation of designing your own abstract data type interface. Just like any checklist, it's something that you should simply go through one by one and take note of. Not all of the items in this list are hard and fast rules. Some of them can be violated from time to time, but in general, you want to make sure that you understand if you're violating one of these rules, and if so, make sure that you've really got a good reason for doing so. The point of the checklist is not to be a hard and fast, inflexible way for you to put things together, as much as a guideline to make sure that you've actually thought through some of the important issues involved in designing your own class. We're going to move through this particular checklist rule by rule, and I'll try to comment a little bit on each of the items in the checklist and give you some examples of why I think this particular thing is something you really should be thinking about whenever you are faced with the task of creating your own abstract data type interface. Our first rule is the interface complete. By complete, we mean that all the operations that you need in order to accomplish whatever application you're trying to support with this abstract data type, all those operations are actually present and available in the interface. And the simplest way to determine this is to try to think ahead as to what your application is going to require and ask yourself if you can at least sketch out a plausible way to accomplish that particular application working through that interface. For example, your textbook, the Horseman book that is, spends some time talking about a class called day, representing a day with a given year, month, and date. We might instead call this a date reflecting its relationship to a calendar. Now, the textbook gives a Java version of this. I'm showing you my closest possible C++ translation because we're still dealing primarily in C++ at the moment. And my C++ translation of this starts with the declaration of the class day, a rather typical constructor for the day class, in which we can give it a year, a month, and a day. We have some accessor functions to get the year, get the month, and get the date, the day of the month, that has actually been stored inside a given day object. We also have some operations for manipulating these dates. We would like to know what day is the day n days away from this one. And so if I was to say, well, today is August 30th, if I add 1 to that, I would be August 31st. If I add 2 to August 30th, I should get September 1st, and so on. The inverse of that is the days from function, which lets me say from this day, let's say that this day is September 2nd, I can say how many days from some other day. And so I should be able to say, for example, that August 30th is 3 days away from September 2nd. So you'll notice that add days takes the current day, adds an integer to it, and yields up a new calendar date. Days from, on the other hand, takes your current calendar day, some other calendar day, and gives you an integer representing how many days are away from each other. This is sort of like addition and subtraction of dates, except you can't really add and subtract days directly in a meaningful fashion. That is, if I tell you today is September 2nd, and I say, what is September 2nd, 2012, plus August 30th, 2012, well, that really doesn't make any sense. Addition and subtraction, to the degree that they apply to days, is sort of an asymmetric thing. You can add an integer number of days to a date, or you can subtract two dates from one another and get an integer number of days that separate them. But it's not like adding integers to get integers and subtracting integers from one another to get integers, or subtracting floating point numbers from one another and getting a floating point number. Calendar arithmetic doesn't work that way. We also have a couple more functions here. One is to compare the current day to some other day and say true or false, this day comes before that other day. And then true and false, this day is the same day as some other day. So that's our interface. And the question is that interface complete? And in order to answer that question, I would have to think about the kinds of things I actually expect to do with this day interface and say, is it possible to do them? And if I was anticipating, for example, writing some code like this, if D, presumably of type day, is the last day in its month, then we will set payday equal to D. Can we actually do that with our current interface? And the answer is yeah, actually I can support this test. Is D the last day in its month? All I have to do is try adding 1 to a given day and see if getMonth changes the value it returns. If so, that was obviously the last day in its particular month. So this is accomplishable. I might not want to actually write it that way in my application. I might want to write a utility function to answer the question, is last day in month? But nonetheless, I can write that given the interface. So it is complete. It would enable me to write that particular application. On the other hand, suppose I was anticipating something like this. While payday falls on the weekend, move payday back one day because we don't actually issue checks. If, say, we normally pay people on the 15th of the month and the 15th is a Saturday, then we might issue the checks on the 14th instead so that we can actually do that on a day that is a regular work day. Can we support that through this particular interface? Well, no. Actually, we can't, because in this whole interface, there was nothing in here that let us get access to the day of the week. We can get the year, we can get the month, we can get the numeric date, the day within the month, but we can't actually get to the day of the week. And that means that there's no way to actually support this notion of, is the payday on Saturday or Sunday? And so that represents an instance where if this is an application that we want to support with this particular ADT, we'd have to say that the ADT interface is not complete for this application, that in fact it's going to need something. We'd probably want to consider adding a new function to that interface to actually get out the day of the week, Sunday, Monday, Tuesday, or whatever. Our second rule in the checklist is in some ways the reverse of the first rule. Instead of worrying about completeness, we can also ask whether there are functions that are redundant or functions that can be generalized. Redundant, of course, means that we've got two or more functions that do essentially the same thing. And redundancy is something that can make an interface more complicated than it needs to be. On the other hand, sometimes we'll tolerate a certain amount of redundancy just as a matter of convenience for the programmer. Maybe having the same function overloaded to take slightly different parameters. That might be redundant, it might also be convenient. So like many of these rules, this is not something that says, oh, this is a hard and fast rule, no redundancy, but something for you to recognize when you have it in your abstract data type. Think about it. Think about whether you really want it or not. Functions that can be generalized, on the other hand, represent things that we've written to be overly specialized, and we might want to consider replacing them with a more generalized version that would offer us more flexibility when it's time to write our applications. For example, our current interface, we might have a print function. And I see this in a lot of student-designed abstract data types all the time. Now, I like the idea of having a print function with every abstract data type. In fact, we'll talk about that a bit more in one of the later items in the checklist. However, this print function, I would argue, is overly specialized. The fact that it doesn't take any parameters means, well, where is it printing to? Presumably it's printing to something like standard out or cout, whatever was the default that the designer had in mind when they wrote that. And that's a good thing, but what if you want to actually print to the standard error stream, CERR, instead? Or maybe you want to print into an output file that you've opened an OF stream on. Well, in that case, this function is not going to do it for you, and yet it would be so easy to generalize that by simply giving it a parameter, which is the place to actually print to. At that point, it becomes a much more generalized, much more usable function, and so I would say replacing this by that is a net win for us in terms of our ADT design. Now, of course, most C++ programmers are actually used to writing their output like this rather than that, but we can take care of that by adding our own output operator, operator double less than, which takes the output stream and the day to write. And in fact, probably what we'll wind up doing is actually invoking our new print function inside there. It's just that the operator form is somewhat more convenient because it lets us actually write our output in the way that we're more used to. Is that redundant? Yes, it is. Is it convenient? Yes, it is. So I'd probably leave that bit of redundancy in my abstract data type. Notice that I can't necessarily get rid of this function. Why? Because the operator here is not inside the class. Notice that the class declaration ends here. You cannot make output operators a member of the class that they're printing out, and that means that in general they don't have access to the private data structures that actually implement the ADT. And so this operator very likely would not be able to do the printing on its own if we did not have a public function of some kind to help it out. Third point in our checklist. Have you used names that are meaningful in the application domain? The important part here is that bit about in the application domain. Hopefully, ever since you started programming, people have been telling you that you should use variable names, type names, and so forth that are meaningful. But as members of the class of object-oriented designers and programmers, we believe that it's important that our programs simulate the real world, that their designs reflect the structures that we find in the real world, and consequently we believe that our names should reflect things in the real world. An application domain is just a multisyllabic form of saying the real world, specifically the part of the real world that we're actually simulating with this particular program or that we're serving with this particular application program. The key is that good variable names should make sense to anyone who actually understands the application domain. It's not enough to say this thing is meaningful because it is meaningful in terms of what the program does internally. You want it to be meaningful to anyone who joins your programming team who understands the application domain but hasn't started reading your code yet to see how you're actually doing things. That means that when they come to the part of the code that you're actually using these in, they can read the name, understand what's going on. So the purpose of this is to make sure that, in fact, this name communicates to people who join your particular team. Here I've got an example of a class, book, and we've already looked at variations of this class in some of the earlier lessons. And I have my constructors, I have my destructor. Some of the earlier lessons talked a bit about why we need the assignment operator and so forth, and I'll also be addressing that a little bit later on as well. We have our various functions to provide access to our attributes, title, author, identifier, and so on. Now, of these, if you told someone that you were working with books, and you said, and I've got a function that lets you get the title, they'll understand what the title of a book is. If they've ever seen a book, they understand that books have titles. They'll understand the purpose of a getAuthor function. Will they understand the purpose of getIdentifier? Well, not really. Programmers might intuitively understand there is a need often to have unique identifiers for things. That doesn't necessarily mean that they'll know what the identifier is or why you need it in this particular context. And certainly if you were reviewing this with a librarian or a bookstore manager or someone else in an application domain for which you would be creating this book ADT, they wouldn't necessarily have a good idea of why you were using an identifier. On the other hand, we know that most books do have a unique identifier. It's called the ISBN. That little number with all the digits separated by dashes that you find typically printed on the back cover. And that's a unique identifier for that particular book. And so it makes sense that probably our implementation of this identifier attribute up here is probably going to be based on the ISBN. So why not use that as the name? Because that idea of an ISBN is meaningful to people who know books, while the generic notion of an identifier does not carry that kind of meaning. So you might have intended to use the ISBN for this identifier all along. In fact, I'm rather assuming you did. My point in this item of the checklist is use the name that will be in fact meaningful to people in the application domain. In fact, if you weren't planning on using the ISBN, the fact that you would then have needed to create something in the public portion of your class with what is clearly not going to be a meaningful name in the application domain should have been a warning. Something's wrong here. Maybe you really do need something that's artificial, but the natural reaction in that circumstance should be go back to the application domain and look around for something that actually fits there. Our next item has to do with preconditions and assertions. And there's actually two parts to this. Part one is, are the preconditions and assumptions well documented? Now, a precondition is a special kind of condition pertaining to functions. A precondition is a condition. It is a Boolean expression of some kind. It represents some circumstance that the person calling a function must be sure is true before they make the call, if in fact they expect the function to do anything reasonable. What happens if you call a function that has a precondition and you violate the precondition? Well, anything at all. If you were calling, for example, a square root function, you would expect that you should be supplying non-negative numbers to that because square root of a negative number is not actually supported. That is an example of a precondition. It is something that you, as the person calling the function, are expected to make sure is true. It's not the obligation of the square root function or the person who wrote the square root function to make sure that you call it with only non-negative numbers. In fact, there's no way that the function can guarantee that or that the program who wrote the function can guarantee that. At most, they can check for it and complain if you violate that expectation. But the precondition itself is an obligation on the caller, not upon the function being called. So one of the things you want to look at as you design ADTs is to go through your list of functions and say, do any of these have preconditions? Now, you'll find different styles of writing preconditions. For example, there are authors out there who would take something as simple as getYear here and say, well, the precondition for this is that the day object must have been properly constructed. Well, yeah, that's true, but the truth is that's a universal precondition. If you have garbage in an object, then nothing's going to work. So the object being properly constructed, in other words, it's not garbage, it's not random bits, is a precondition for anything. There's no point in documenting stuff like that. If you document preconditions that have to be documented in every function you write, people stop reading your documentation. And that means they won't pay attention when you have a more realistic precondition. So no, there's not a real precondition on that. How about add days? Does it make sense, for example, for n to be 0? Well, sure. I don't know why you would add 0 to a current day, but that should give you back the same day. And you can imagine that if n was something that was computed through some larger calculation, maybe sometimes, 1 out of 100 times coming around a loop or something, n would be 0, and you certainly don't want the function to crash in that. So I would say it's perfectly acceptable to feed this a 0. Is it acceptable to feed it positive and negative values of n? Sure. If I want to talk about what is 3 days after this date, or 4 days before this date, both of those are legitimate, and they just represent different, signs on this value n. So I'm good with any integer value of n in here, really. So I don't see any particular restriction there. So are there any functions in this interface that have preconditions that we actually would want to guard? And I would say, yeah, probably that constructor. I would say if you're going to build a calendar date from a year, month, and date, that it's reasonable to expect that those have been put together with legitimate values. For example, we might say our month should be greater than 0 and less than or equal to 12. The day part should be greater than 0 and less than or equal to however many days are in that particular month in that particular year. Because of leap years, you have to include the year in that particular calculation. That's an example of a precondition. Now, what should this constructor do if you call it with, let's say, a negative value for a month? Well, the answer is anything it wants to. We're not actually specifying anything at the moment for what to do if you're given invalid values. It is possible to write a specification that says, if you give this thing a negative month, it treats it as January. But now, once you've done that, you've actually said it is legal to give this constructor a negative month because you've said that it will, in fact, do something reasonable and expected in those circumstances. So that won't always be true. Sometimes programmers do say, I expect you to supply legal values to this, and the precondition is the description of what they mean by legal inputs to that particular function. This precondition does illustrate some good properties of a precondition, and one thing to worry about. Preconditions are almost always expressed in terms of either the values being passed in as parameters or possibly as values that have been previously stored in the object. With a constructor, there are no previously stored values, since the whole point of a constructor is to construct something for the first time. But in general, if you think about an ordinary function like, say, add days, this has as inputs whatever you've passed here, and also as an input whatever day you put on the left when you type something like today dot add days parentheses 12. So the inputs to a member function are always the thing on the left plus the stuff in parentheses, and preconditions should generally be expressed in terms of those inputs. Why? Because the precondition is something that the caller is supposed to make sure is true, and the caller is supplying those inputs. That's what they have to work with. You want to try to make sure that the precondition is something that the caller can actually check here. And that gives us a little bit of a problem with this days in month here, because although it's a clear enough concept, it's not clear how in practice the person who wants to construct a new day would call that, unless maybe we consider possibly adding that as a new function in our interface. And that might be a good thing to do so that it actually becomes possible for the person making the call to that particular function to actually check that particular thing. In a similar vein, I would say you need to be very, very careful to never, ever take something out of your private data area and write that into a precondition. Why? Because if you write a precondition in terms of values that are currently stored in the private members, there's no way for the caller to actually check those. They're private. So it's always crucial that the things that the concepts that you mention, the variables that you use, inside your preconditions always be something that is going to be available to the caller. Otherwise, you're cheating. You're telling them you have to check this before you make the call, and then you're telling them that the thing they check involves stuff that they can't actually get their hands on. Now, that's not the most general form of the precondition here. Our specification up here says that the day represents a day with a given year, month, and day of the Gregorian calendar. The Gregorian calendar started up on October 15th, 1582. That was the first day of the Gregorian calendar. And so we might actually want to say not only should the month be in the range 1 to 12 and the date be in the range 1 to however many days are in the month, but that in fact the year either has to be after 1582, or if the year could be 1582 as long as the month is after October, or the year could be 1582 and the month be October as long as the date is the 15th or later. And so that would actually be a full precondition for that, because any rules that we are likely to come up with for how we implement add days and days from probably rely upon us sticking within the Gregorian calendar. And anything that would take us earlier than that doesn't work. Has no meaning officially in this abstract data type. You will note that I do favor writing preconditions as Boolean expressions in the actual programming language that you're using. And the reason for that will become clear in just a little bit when we talk about enforcing those. Here's another example of an abstract data type, a mailing list. I think this has come up in some of the earlier readings as well. And our mailing list has the usual constructors, destructor, assignment operator, and so forth. Main things we do with mailing lists, we add contacts to them, a contact being a name, and then either, this might be an email address or physical mail addresses. So a contact would include that name and address. We can remove contacts as well. And we have a function here, contains, that tells us whether or not a given name is somewhere in our mailing list. And we have a getContact function that, given a name, returns a contact. And then we also have something to merge another mailing list into this one and to say how many contacts we currently have in the list. And the question that I want to ask is, what precondition, if any, would you write for the getContact function, which is this one right here? Do we need a precondition? Well, are there any circumstances in which, when we called this function, we could not reasonably expect it to do what we want getContact to do, which is to find and retrieve contacts? And yes, there is a condition in which we would have difficulty, namely, if this particular name did not occur anywhere in the mailing list, was not there in any of the contacts. Now, is that a problem? It's not a problem for this, because the contains function is just returning true or false. And so we would expect it to return false if we give it a name that's not in the mailing list. However, the getContact function is expected to return a contact, and it's not clear exactly how it could do that if we give it a name for which we don't have a contact. What's it actually supposed to return here? Now, if we were returning contact star, a pointer to a contact, yeah, we could say, well, we'll return null if the name isn't in there. But we're not doing that. We're returning an actual contact. So what do we do about that? The answer is it's not really a good contact we can return, so it's a precondition. And the precondition in this case is it should be true that this name is contained in the ADT. Notice that what I'm doing here is, in the precondition, I'm actually invoking a function that is part of the interface of the mailing list, which is fine. It's in the public part of the interface of the mailing list. That means that someone who we are saying has the obligation to check this before calling getContact can actually do so. They can use that function to check and see if, in fact, it's legal for them to invoke getContact. That's what we want out of a precondition. The second part of this particular item is, have you used assert to guard the inputs? An assert statement is a statement in C++ which takes a single argument, which is a Boolean condition. And the point of making an assertion is to say, we believe this condition should be true unless, in fact, there's a bug in this code. And most often, for our purposes, when we're using asserts to guard precondition, that means that the bug has got to be in the caller. By guarding a precondition, what we do is we write it as one or more assert statements. And so here what I am doing is I am saying in my implementation of the constructor for the day class, I will actually check, is the month that I've been supplied in the range 1 to 12? Is the day in the range 0 through 31? Is the total day something that can be expressed in the Gregorian calendar? If all those assertions are true, then I'll go ahead and do whatever it is I'm going to do to actually implement this particular, to construct this particular day. Here's another example of guarding a precondition. We said that our contact is only valid if, in fact, the name is in the list or is in the mailing list. And so what I've done here is I have a loop that runs through and tries to find a node in a linked list in which the contact has the desired name. And upon exiting that loop, I assert that, in fact, we didn't run off the end of the list, and that, in fact, we stopped because we found a matching name, which is another way of saying, yes, the mailing list does contain this particular name. Now, both of these are examples of guarding a precondition. What happens if someone makes a call to this and they give us data that is not true? What happens if someone calls the day constructor and gives us a negative month or a month of 22? Well, what will happen in most cases is that the program will crash and an error message will be printed more or less to the effect of assertion violated in some file name day.cpp at some particular line number, and that line number would actually identify the location of this assertion statement. It is possible to turn assertions off with a compiler flag so that things don't crash, and there are some people who do advocate leaving your assertions active while you're testing and debugging and then turning them off in production code under the theory that people don't like seeing their programs crash and seeing error messages that were clearly intended for a programmer appearing on their screens. That's certainly true. People don't like that. Of course, people also don't like programs continuing to run in circumstances where the calculations have obviously gone wonky and corrupting their files or corrupting their database afterwards by writing known bad information into them. So, I'm somewhat dubious about the notion of switching off assertions. The truth is, if you violate an assertion that's been put in there to guard a precondition, that violation means there's a bug in the application code. It is calling this function with illegal input, and you continue running the program at that point at your own risk, frankly. We've all heard these stories of programs that have gone crazy and some poor senior citizen somewhere getting a telephone bill for millions of dollars in some month. And usually that's a pretty good indicator to me that someone turned off all their internal checking for the production code. And so when something went wrong, they didn't actually shut the program down and instead let it generate obviously bad output. Now, some people would argue that I've done a disservice here, that in fact, instead of putting this assertion in here and aborting the mailing list code, that instead what I should have done is just use a good old-fashioned if statement for the exact same condition, and if it was satisfied, do the normal thing, and if it's not satisfied, return something innocuous. And let the calculation continue. This goes under various names. Some people call this making the code tolerate errors. Some people call it making the code robust. But I generally don't believe in doing this. At least I don't believe in doing this unless it's part of the documentation saying that the function is going to do this under these circumstances. Reason being, again, if the precondition has been violated, that means there's a bug, and the bug is not something you can handle here because it's in the application. And you don't know how pervasive that bug is. You don't know just how messed up the current data state is. So for you to try to fix it in this very narrow vision place that you're sitting at inside this particular function, inside this particular mailing list class, you've got no hope of fixing it. You don't know if, for example, returning this value really is an innocuous thing to do, or whether it's going to make things worse. In addition, programming this sort of thing in has a really bad effect on testing and debugging. If, in fact, you are testing your program and you do something like that, what you are actually doing is saying, guess what? Your test did exactly what it's supposed to do. It showed that there's a bug in the application. Oh, I'm going to hide that from you. I'm going to try to, in fact, let this program run and maybe hide the existence of this bug from you. It's defeating the very purpose of the test to, in fact, hide the fact that you know at this point something has gone wrong in the application. That kind of thing, hiding bugs like that, can lead to plausible but incorrect output, eventually corrupting long-term databases, files, leading to disaster in the long run. From my point of view, you're almost always better off announcing that a precondition has been violated and shutting the program down at that point. All right, next item in our checklist. Are the data members private? This is a very simple one compared to the one we've just gone through. We want all the data members to be private, and one reason for that is because you may want to change those data members later. For example, for this day class, there are at least two very plausible ways to implement it. One way is to have separate integer variables for the year, the month, and the date, in which case these functions, for example, just directly return the values of their respective variables. The constructor probably just stores those three values, a year, a month, and a date, into the year, the month, and the date. So implementation of those things are very simple. On the other hand, for that particular implementation, add days and days from actually become real headaches to try to implement, because the calculations for these have to take into account all kinds of nastiness regarding what happens if you try to add some number of days that takes you across a leap year. Just ugly, ugly calculations at that point. And so these things become ugly, they become slow, but these things are fast. Another implementation, an alternative to having these three data members, is to have a single data member, which is the number of days since the start of the calendar, which for the Gregorian calendar, we've already said, is October 15th, 1582. And so one integer instead of three means that adding some number of days to that is just adding n to days since start. Figuring out how many days away some other day is from this one involves subtracting other dot days since start from this days since start. So the implementation of these two functions becomes very fast, very simple with that particular data structure. On the other hand, the implementation of these three functions now becomes correspondingly complicated, because trying to figure out what year it is, if you are, let's say, 10,000 days past October 15, 1582 is now fairly complicated, and it has to include some calculations that take into account how many leap years would have been in that period of 10,000 days since that particular year, and so that gets ugly and gets correspondingly slow. So which of these is the better data structure to use? Well, really comes down to which of these things are you doing more often. If you are implementing a spreadsheet that does calculations over dates, you may want to be very sure that those calculations can run very, very fast, and so you would prefer that implementation. If you are implementing something where you are mainly just taking dates in, storing them, and formatting them for I/O, then in fact you'd probably prefer that these operations be faster and simpler. When you start getting into circumstances where you're not only dealing with days but times as well, and you have to start dealing with maybe different time zones and things like that, seconds since starts to look a lot more attractive in order to handle time zone calculation. So a lot depends upon the needs of the application, and it's not unheard of in the later stages of engineering an application to make a change and say, you know, we started with this, but it turns out we are mainly just storing dates and not calculating on them very often, and so maybe we should favor making these things simple and fast, and that will mean switching to this other implementation. You know, that's a perfectly valid thing to do, and you want to leave yourself the option of doing that. Making sure that all your data members are private gives you that flexibility. I can change from one of these data structures to another. Doing so requires me to reprogram these things, certainly, but I can do that and I won't have to touch any of the code in the application, because if the application ever tried to directly access any of these, it wouldn't have compiled in the first place. The application is only able to work through our public interface. Now, if you're going to make those data members private, of course, you need to actually provide access to the data that they're storing in some fashion. And we use this term attribute for things like the year, the month, and the date. Things that just from a conceptual point of view we think of as data components or data stored in the object. Now, that doesn't mean the implementation has to actually treat them that way. In this particular data structure, for example, year, month, and date are not actually stored in the day. Nonetheless, from an interface point of view, we think of a day as a combination of those three data items, and so we refer to those as the attribute or the attributes of a day. And we want access to those attributes. And there are two styles for providing such access in C++. One is the one we just saw, in which we do get and set, or sometimes get and put functions for each attribute. And if we're actually storing the attributes as individual data members, that leads to a very simple implementation. There's another style that you will occasionally encounter, however, in which instead of putting get and set out in front of an attribute, we just have a function which is the attribute itself. So if we thought for our mailing list contracts, for example, that the attributes were the name and the address of each particular contact, here I've done the address in the get form. Here, however, for the name, I've used the alternate style, and I wouldn't mix these in one ADT like this. Normally, I would do one or the other. But in this one, I say, if you want the name, just use a function called name. And because I return in this one, not just something of type name, but a reference to name, that means I'm actually returning the address of the particular name stored inside this contact. Because I'm returning an address, I can not only look at that name, but I can store into it as well. And so the nice thing about this style of providing access to attributes is the ability to use the same function really for both getting and setting. The disadvantage is it's almost impossible to do this, not impossible, but almost impossible, certainly difficult to do this if you actually don't store the attributes as separate data members. If you were doing something like the days since implementation of the day class that we've been looking at, it would be very difficult to do this style of access for the year, month, and date. Next on our checklist, we're about halfway through now. Does every constructor initialize every data member? Very simple. You have to look and see how many data members you've got. One of the purposes of having a constructor in the first place is to make sure that this object, when you declare it, starts off its life as being well formed. It doesn't have any random bits left behind in it that just happen to be left over from whatever, code or data used to be occupying that particular block of memory before you created this new mailing list or whatever it is. And so what you simply want to do is go through all your data members. For the mailing list here, I've got 3 data members. I have an integer for the size of it and pointers for the first and last nodes in the linked list that I'm maintaining. So what I want to do with that is I want to look at the code for each of my constructors up here and make sure that somewhere in that code I find initialization of each of those 3 data members. And so if I looked in my implementation, I found this as my implementation. As for the first constructor, I can just look and say, yep, first, last, the size, that's all 3 data members, all 3 are initialized. Here, first, last, the size, yep, all 3 of those are initialized. So it's a very quick check, but it's a very useful one. Just want to make sure every data member has been assigned some value somewhere inside the constructors. And make sure that's true for each of your constructor if you have multiple constructors, as in fact we do in this particular class. Number 7, describe the default constructor. Now what do I mean by describe? I don't mean tell me what the definition of it is. I mean describe how you have handled it in this particular ADT. And there are really 4 options here. Remember that the default constructor is the constructor that can be invoked with no parameters. And it's useful because of things like its common use to initialize arrays in C++. So you have 4 options. You can say, I let the compiler generate one and I'm happy with it. Or you can say, I wrote my own. And hopefully you're happy with it if you wrote your own. Or you can say, I don't believe this class should have a default constructor. There's no logical way to initialize a value of this type without supplying some kind of information through parameters. Or, very rare, sometimes you want to have a default constructor, but you don't want to allow any code outside of your ADT to invoke it. What you do then is you go ahead and declare a default constructor, make it private, so that you have one that you implement on your own, but no one else can call it. So remember, the default constructor is the constructor that takes no arguments. This declaration, for example, uses the default constructor for string. And what makes that useful, what makes the default constructor special, is not that it takes no arguments, but that it gets used in some special places. Most importantly, that it gets used when you declare arrays of things. That is, if I have an array of 5,000 strings, then actually what happens is the compiler not only generates code to allocate that array, it also generates a loop to go through each of the 5,000 elements and initialize each of them with a call to the standard string default constructor. Which means, by the way, that creating very large arrays like that of class types can often be a very time-consuming process in C++ and may be a good indicator that you should look for a more sophisticated data structure. Remember, if you create no constructors at all for a class, then the compiler is going to generate a default one for you, and you have to think whether that's okay. In the contact class that we were looking at, we didn't have a default constructor. We had a constructor which took a name and an address. Because we have provided a default a constructor of our own, the compiler will not generate a default constructor for us. If we decide we want to allow for arrays of contacts, then we would actually have to go ahead and add that. And it's not too hard to do that if we assume that everyone who programs an ADT follows the same checklist. Then presumably whoever implemented the address class and the name class provided them with good default constructors. And so we can actually provide our own by just saying, it's okay, let those things fall back to their own defaults. For the mailing list class, we did provide our own default constructor, and that default constructor was designed to set the pointers to the linked list nodes to null, indicating that initially we have no linked list, and set the size of a newly constructed mailing list to 0. Next, describe the big three. And again, when I say describe, I don't mean define it. I mean tell me how you did it in your ADT, or think about how you did it in your ADT. Recall that the big three are the copy constructor, the assignment operator, and the destructor. And it's important to recognize that for each of those, if you don't provide your own version of them in your class, the compiler is going to generate one for you. And you may or may not like that version, because as we've seen in earlier lessons, that version is going to be centered around the idea of shallow copying and of do nothing if you are a destructor. The rule of the big three, we've seen, says that in general, if you provide your own version of any one of the big three, you should provide your own version of all three. The reason being that the circumstances in which you do not trust the compiler-generated version of the copy constructor essentially comes down to, I don't trust the compiler's version if I have data members that are pointers, and I don't intend to share the things being pointed to with other objects. The circumstances under which I would not trust the compiler-generated version of the assignment operator are if my data members include pointers and I don't intend to share the things pointed to with any other objects. And the circumstances under which I don't trust the compiler-generated version of the destructor is, again, if my data members include pointers and I don't intend to share those with any other objects, and therefore I'm responsible for deleting them when in fact this particular object is being destroyed. So we tend to not like the compiler's version of these things under the exact same circumstances. Hence, the rule of the big three says, if you provide your own version of any one of those, you should provide your own version of all three. That means that when we come to this item in the checklist and I say describe what you did with the big three, this comes down to really three possibilities. You've decided the compiler-generated version is acceptable for all three, and you're happy with that, or you have provided your own version of all three because you didn't like the compiler-generated version, or you've decided that you don't even want to allow objects of this type to ever be copied, in which case you have a little bit of a problem. How do you keep the people from invoking a copy constructor and assignment operator? You can't do it by simply not providing one, because if you don't provide one, the compiler generates one for you. What you actually have to do is you have to provide a copy constructor and assignment operator, but you have to declare it as private. That means they don't actually have to do anything useful, because no one's ever going to be able to call them. So, compiler-generated versions are wrong in circumstances when you wouldn't want to be doing shallow copying, and for the destructor, when you are holding resources that need to be released. Those boil down, as I said, to your abstract data type as pointers among its data members, and you don't want to share the objects that are being pointed to. In the case of our contact class, if we review the interface to this, you will see I have a constructor here. I don't have a copy constructor. I don't have an assignment operator. I don't have a destructor. So in the case of the contact class, the compiler is going to generate those for us. And I'm pretty happy with that. The compiler will generate a version of a copy constructor as if I had written this. Namely, in order to make a copy of a contact A, what you do is you make a copy of A's name and put in the name of the new copy, and you make a copy of A's address and put it in the address. That's fine. Now I'm assuming here again that everyone is following this checklist, which means that the name class and the address class, someone has also thought about this and made sure that their copy constructors actually work properly, either because the compiler generated version was appropriate or because they provided their own. But we do assume that other ADTs we use, follow these same rules. Similarly, for the assignment operator, the compiler is going to generate something along these lines. It's going to say, all right, if you want to assign some other contact A to this contact, what you will do is first assign A's name to this contact's name, then assign A's address to this contact's address, and that's it. And that's good. That works perfectly fine for contacts. The compiler-generated version of the destructor would do nothing. And that's fine because neither the name nor the address is a pointer. Now, when I say it does nothing, it does invoke the destructors on each data member. That's done implicitly. And so if they have been explicitly coded to do something on their own, those will still get invoked. But as the author of the contact ADT, you don't need to do anything in particular. So that, that all works. And that works because none of the data members in the contact class themselves are pointers. Now, one of the things this boils down to is I've actually talked about this in another lesson, so I'm going to move forward from that. In the case of our mailing list class, we do have data members that are pointers, namely the first and last pointers are in fact the pointers to nodes of the linked list, and those are allocated out on the heap. So if we allowed the compiler to implicitly generate things, it would actually just be copying the addresses of the other mailing list, ML. It would be copying the address of its nodes into our mailing list. And that would give us two mailing lists which were sharing the same linked list of nodes. And we've seen in the previous lessons that that's a bad idea because as soon as you update one of those two mailing lists, you wind up corrupting then the other one. Same thing for the assignment operator on mailing list. This copies addresses of existing nodes into a different mailing list, and then the moment you update one mailing list, you corrupt the other. And finally, the compiler-generated version of the destructor would do nothing at all, which means that any nodes we've got sitting out on the heap for our linked list of contacts will stay out there when this mailing list disappears, and so we've leaked memory. So we've seen this kind of thing in our discussions in earlier lessons and recognize that we don't want copying to give us situations like that. So what do? We write our own. In order to copy a mailing list, we start with an empty mailing list of size 0 and null pointers for the first and last, and then we loop around through ML, moving through its linked list of nodes, and for each node in ML's list, we get the contact out of there and just invoke the add contact function. After all, we have to write an add contact function to add new contacts to a mailing list anyway, so let's go ahead and reuse it. Similarly, for assignment, what we would do is we would clear out any stuff that's already in our linked list, then go through the mailing list that we're copying from, ML, loop through all of its nodes, For each node it has, we extract out the data from that node, the contact, and we add it as a contact in this list. So we are not sharing the actual nodes, we're actually making copies of the contacts into a completely separate mailing list in each of these functions. And that's what we want to do rather than a shallow copy. We're doing a deep copy here. Our clear function runs through mailing list, deleting each node in it, and our destructor, when we implement our own, would simply call that clear function, so that each node will eventually be deleted. Okay? Moving on, does your assignment operator handle self-assignment? This refers to the curious possibility, if you're writing your own assignment operators, what would happen if someone wrote this? Now, you might wonder, well, why in the world would somebody ever write something that silly? And truthfully, no good reason to believe that they would write something quite that obvious. But there is the possibility that they would do something a little bit more subtle. For example, you can think of the way that many sorting algorithms work, where you do things like have more than one index running through an array, and then under certain special circumstances you might say, all right, I want to do this. Well, it's quite possible that some circumstances will come up in which I and j will actually be equal to one another, which means that the net result of that is that you actually have done an assignment of one particular object to itself. So because of the possibility of having something like this disguised, you have to allow for the possibility that it's going to happen. And what we expect to happen if you assign a variable to itself is nothing. If you assign an integer to itself, you expect no change in that integer. And if you assign a mailing list to itself, you expect no change in that mailing list. However, we're not careful when we implement our assignment operator, something might actually happen. For example, a fairly straightforward implementation of assignment for the mailing list would be clear out the old list of nodes in this particular mailing list that we're about to overwrite with a copy of ML, then loop through ML as we just described earlier, picking up each contact out of ML and adding it to this mailing list. So that creates a copy of all the contacts in ML. And since we want this to be assignment, it should replace the old value of the mailing list. So before doing that, we will have cleared out any existing linked list in this mailing list. But now what happens if we assign one mailing list to itself? Well, the first thing that happens is we clear out all the nodes in the linked list for this mailing list. And then we're going to try to loop through all the nodes that remain in the linked list for this mailing list. Well, there won't be any. We just cleared them. So we'll actually go through this loop 0 times. And at the end of it, it means that when we assign the mailing list to itself, this has the effect of actually clearing the mailing list instead of leaving it alone. That's not what people are going to expect when they write algorithms like that. So we want to make sure that doesn't happen. And the way that is handled is by actually checking for this action of assigning something to itself. Remember that the this pointer holds the address of the object that is going to be on the left of a member function call, or in the case of an operator, on the left of that operator. And so this is the address of the mailing list we are assigning to. ML is the mailing list we are copying from. And the ampersand, when it's written as a unary operator in front of something, says take the address of. So what we're asking is the address of the mailing list we are assigning to the same as the address of ML? If it is, we're going to bypass all that. If those two addresses are different, then we'll go ahead and we'll do that. But in the circumstance where those two addresses are the same, we are in fact assigning this mailing list to itself. We bypass everything in there and we just jump down to the return statement. So that then becomes an implementation of the assignment operator that is safe for self-assignment. Next item, does your class provide equality and less than operators? Why do we want these? Because really a couple of reasons. Most obvious, sooner or later you may want to use these things with standard container classes like set or map. And those container classes, along with a lot of other algorithms that are provided in the standard library, sorting algorithms and things like that, tend to assume that these things are present. And it's a real annoyance if you're coming along in your programming using some particular abstract data type, and then you decide you want to do something innocuous with it, like say, oh, I've got a list of these and I want to sort them, or I've got a list of these and I want to find out if any of them are duplicates, and you discover you can't do that because you've got no means of comparing them to see if they're the same, or comparing them to see if they're out of order with one another. The compiler is never going to generate these things for you implicitly the way it does with assignment operators and copy constructors and things like that. If you want them, you have to supply them, and because they are so commonly assumed to be present by different elements of the standard library, you probably just want to go ahead and plan on providing them whenever you provide a new abstract data type. In addition to that, we'll see in later lessons that the equality operators get very heavy use when you start doing self-checking tests. And it becomes almost impossible to write good tests for abstract data types if you haven't supported at least the equality test operator on that ADT. And so you will want it for that purpose as well. Now, providing equality operators is usually not conceptually difficult for people. For the most part, we tend to imagine that our data types, two objects of that type, are equal to one another if their attributes are equal. And so if you understand what the logical attributes are and you know how to access them within a member function, then you can write the code, for example, for contacts to say, all right, this contact is equal to the contact on the right if their names are equal and their addresses are equal. And here again, we're making this assumption that the people who have written the other ADTs in our library have followed the same rules. So here I am comparing two things of type name. Here I am comparing two things of type address. We're assuming that the name and address classes also provided equality operators that work in some rational fashion. For things that don't have sort of a fixed number of attributes but are more generic containers like our mailing list, not surprisingly, if I want to compare two mailing lists for equality, I'm going to need some kind of loop that takes me through elements and compares corresponding elements for equality. Now, it's often a good idea if you've got two lists of different sizes, you could get into a nasty thing where you could have the loop and then say, well, did we run off the end of one loop before the other? That's kind of nasty. But in this case, we can very easily say, are the mailing lists the same size? If they're not the same size, then we know right away they can't be equal to one another. So we'll return false. If they are the same size, then we can have two pointers that start at the beginning of each loop. We can loop around and know that when we run off the end of this particular linked list loop, that we will be ending both lists simultaneously, and we know that because we're only going to come here if in fact the two lists were the same size to start with. And so we can loop around doing the usual move forward one step with next pointers each time around the loop. But before we do that, we check to see if the contacts are different. If the contacts are different, then the lists are not equal to one another. And if we do manage to exit the entire loop and never found two contacts that were not equal to one another, we can return true. So equality operators are usually pretty straightforward. Less than operators tend to give people more headaches. The reason being, it's not always obvious what less than even means. If you're hung up on the numeric interpretation of less than, what does it mean to say one mailing list is less than another? What does it mean to say one contact is less than another? If you're hung up on the numerical interpretation of less than, those concepts, may not make sense. But if you remember that one of the primary uses of less than is to put things in order, sorting, then instead of reading this as actually less than, read it as comes before. And suddenly you can think, what would it mean to say one contact comes before another? Well, it means I have a normal way of writing them, say alphabetically by name. And in that ordering, this one comes before the other. What would it mean for one mailing list that comes before? Well, I would have to come up with some way of saying, if I was providing an ordered list of mailing lists, how would I want them ordered? And then working with that particular interpretation. But there are many code libraries, including lots of stuff in the standard library, that does assume that this operator is available. So you want to provide it if you can. The catch, and the thing you need to keep in mind here, is that almost all algorithms that use less than and equal to assume that they make sense together. Specifically, you need to make sure that when you do choose algorithms for implementing these two things, that it is true that for any two values, x and y, of this particular data type, either x is less than y, or y is less than x, or x is equal to y. One and exactly one of those conditions must hold. If none of them hold, things are going to blow up when you try to put stuff in order. That would mean that you have two values of x such that x is not less than y, x is not greater than y, and x and y are not equal. And that doesn't make any sense in most applications. If two or more of them hold, that means you've got something which is simultaneously less than, x is less than y, and simultaneously y is either less than x, or that x and y are equal. That doesn't make sense either. So you want to make sure that you choose your algorithm such that of those three conditions, for any values of x and y, one and exactly one of those will be true at any given time. And that usually means that you want to be careful. Whatever attributes, for example, you're comparing with equality, you will want to make sure that you also pay some attention to them in your less than operator, and so on. For contacts, for example, this would be, I might say, well, when I'm ordering contacts, I want to put them alphabetically by name. But that would lead me to maybe write a less than operator in which I only compare the names. If I look at the fact that my definition of equality says they're equal if the names match and the addresses match, then I know I really need something more elaborate for the less than. I have to say something like, all right, I arrange them alphabetically by name to start with, but if I have two contacts that have the same name, then I'll arrange them alphabetically by address. So that becomes, this becomes the tiebreaker rule among the names. And now I can actually look at these two functions and say, yes, I believe that if this is true, that will not be true no matter which order I write the things in on either side of the less than operator. And I also believe that if this is true, or if that is true, then that will not be true. Can't be, unless the comparison operators for name or address are screwed up somehow. So the important thing in implementing these is to make sure that they're consistent with one another, and that one and only one of these conditions can hold for any two pairs of values. That can be a bit subtle when you're dealing with things like, long list of stuff, but you do still want to do it. So here's my, equality operator for mailing list, which you've already looked at. Here's a corresponding less than operator, which says, all right, if I was ordering mailing lists, first off, if they're of different sizes, I'll say that the shorter one should always come first. If they're of the same size, then I'll go through to the first pair of corresponding contacts that aren't equal to one another, and if the first one is less than, then I'll say that this mailing list is less than the other mailing list. If the first one is greater than, I'll say this mailing list is not less than the other mailing list. If neither of those is true, they must be equal, and I'll go around the loop another time looking for a contact that isn't equal, or a pair of contacts that aren't equal. And if you study this hard enough, you should be able to convince yourself that for any two mailing lists, only one of those three conditions can actually hold. All right, number 11, does your class provide an output routine? Looking at some of the classes we've been talking about here so far, I can see that for this implementation of contact, yes, I've provided an output routine down here. For my implementation of mailing list, yes, I've provided an output routine down here. So I have done this. Why have I done it? This is not so much to support applications. Different applications almost always have their own particular output formatting requirements. It's very, very rare that an output routine that you provide for an ADT that you program this month will turn out to be the right output routine for printing that particular ADT in an application that gets written next month. That's one of the reasons why we have so many different application programs running around, is often because we just want the output in different formats. The reason we put this in there is because think about what happens when you encounter a bug and it's time to debug your code. What do? You start printing stuff out. You start inserting debugging output into your code. So suppose that you are debugging some application that uses mailing lists and contacts. You suspect that deep down inside some loop in your application code that things are going wrong. What do? You go into the code for that application and you start printing things out. One of the things you want to print out are maybe a couple of contacts or maybe the entire mailing list that's being manipulated at that point. So you insert some code that says something like, CERR, let's print out mailing list 12. And you do a quick recompile and try to, hoping to run the program quickly and see what's happening deep inside this algorithm, and the code doesn't compile. Why? Because you didn't provide an output operator when you wrote the mailing list ADT. So what do you then do? You now have to say, well, I can't print this. I need to write a print mailing list function. So here you are, you're trying to do a print mailing list function because it wasn't provided for the original ADT. And that means, what are you doing? You're writing code and code and code. And what's likely to happen? This new code you're writing may itself be buggy now. You may have introduced brand new bugs just for the purpose of being able to produce debugging output. This is not the way to go. The last thing you want to be doing at a time when you're trying to debug some other program is to start having to add code to other ADTs that you thought were implemented a long time ago. So this is one of these cases of, like your mom used to tell you, you'll be happy someday that I made you do this today. You may not like it now, but someday you will come to appreciate this. So that's what's happening here. You may be unhappy about providing output operators for your ADTs now, but someday when you're writing the code that uses them, you'll be so happy you did. All right, because you will be able to have a flow in which you continue debugging your later applications without having to stop and write up a whole bunch of new code and maybe introduce new bugs at the time you're doing so as you're debugging. Final item in our class list. Is your class const correct? You're probably aware that the keyword const is used to declare constants in C++. But it also has a couple of other important uses. One is indicating what parameters, among the parameters you're passing to a function, which ones that function is going to look at, but not change the value of. One of the first things I want to know whenever I'm calling a strange function that has a long list of parameters is which of these parameters are inputs and which are outputs. And when I see a const on one, that tells me it's an input. And so that's an important clue for me. The other thing that const is used for is as a documentation for member functions to indicate which member functions I can call in my usual member function style of saying something like x.member function. And if I call this, will it in fact change the value of x or not? And having a const on the declaration of that member function tells me that no, it won't change the value of that particular member function. And that's useful for me. Also turns out to be very useful for the compiler. The compiler uses that information to help it generate more efficient code. It's used during optimization, for example. But it also allows the compiler to detect and warn me about a lot of very common programming mistakes, such as my trying to use a function that will change the value of something in a context where I'm not allowed to change it or have promised not to change it. This adds up to a notion of classes being const correct, meaning that a class has made proper and maximum use of this ability to label things according to whether or not they're expected to be changed. A class is considered to be const correct if any formal parameter that logically you do not want it to be changed by the function, if all such parameters are either passed by copy or as a const reference, meaning const type name followed by ampersand. So you can pass it by copy or you can pass it as const reference. Second, every member function that does not alter the object it's applied to is declared as a const member function. So in my contact class, for example, looking at this, I'm going to label with yellow any parameters that have been passed by copy, with the purple any that have been passed as const reference, and I'll use blue to highlight const member functions. And just looking through my functions here, you can see contact, the constructor, passes the name and the address by copy, and that makes sense. If I create a new contact and I pass it a name and address, I don't want it changing the name and address that I actually passed it back in my caller routine. So it makes sense I would not want those to be changed, and I've indicated that by passing them by copy, which is acceptable. Here I've got the getName function. Doesn't take any parameters, but I have marked it as const, meaning that when you call getName on a contact, it will not change the contact that you are asking for the name from. And that should make sense. In fact, almost always, if you have something that is get, you should mark that member function as const, because that is your promise that whatever you actually put in the body of that thing will not change the particular ADT object that you're applying it to. By contrast, setName does not have a const marking out here, which means setName is not promising to leave the contact alone, and that makes sense, because what do I mean by setName? I mean change the name of this contact to this thing. And so it does change the object it's applied to. On the other hand, it does not change the name that the caller passed to it. So the caller can rest assured that that name will still be the same thing it was before the call and continue using it internally for whatever its own purposes are. Down here we've got an example of passing something as const reference. And that again is a promise that when you compare two contacts for equality, you are not going to change the value of the particular contact that you wrote on the right of the operator. You're also not going to change the value of the contact on the left of the operator. That's what the const out here means. Why do I sometimes pass things by copy, and why do I sometimes pass them as const references? Well, actually, I probably should have done a lot more const references in this particular interface than I did. In general, either of these, the by copy or the const reference, is sufficient to say this is input only to this particular function. And I'm not going to change the value that was actually being passed in here. So either of those work. When you pass things by copy, you now know that means that the copy constructor is invoked to actually create a new distinct copy of that thing. And for primitive types and things that have only a few bytes worth of data, that's an okay thing to do, to make a copy. When you pass things by reference, whether you pass them by const reference or regular reference, you're only passing the address of the thing back in the caller. So if in fact a contact involves lots of bytes worth of data, or involves a data structure that could take a long time to make a copy of, you're probably more efficient if you pass the address. On the other hand, if the things you're passing are relatively small and easily copied, passing the address means that all of the code inside the function body that uses these things has to do an extra address dereference. And so basically it comes down to how big do you think these things are likely to be and how expensive do you think they're going to be to copy. Integers, floating point numbers, and primitives are almost always passed by copy rather than by const reference. It's just faster to manipulate them if you're not manipulating them as references. On the other hand, most data types, most structs and classes that you will program, you're probably working with a reasonable number of bytes of data. You're probably actually better off passing them as const reference just to avoid the overhead of making a copy. And so probably if I was actually writing this, I would not pass this by copy. I would not pass this by copy. I'd pass it as a const reference. But I'd still be const correct because either of these is an acceptable way of saying these are inputs only. Here's a similar thing for the mailing list. Obviously, if I'm writing my own copy constructor, I want to pass a const reference because if I pass it by copy, then I need to make a copy in order to invoke the copy constructor, and that puts us into a infinite recursion, which is not good. You can see most of my inputs are const references. The containment test, is this name in the mailing list, is a const member function. It doesn't change the mailing list to say, is this name in there? Getting a contact from the mailing list does not change the mailing list when I try to get a contact that's in it. On the other hand, here we've got the merge function, which takes a mailing list and merges it with this one. Now, if I was just looking at this merge and said, oh, I've got a mailing list, I've got some other list, which one is getting the merged content? How do I know which one? I know it by looking here. This tells me that the other list is not going to be changed, and the fact that I haven't written a const out here means that this mailing list will be changed. And so the answer is, when I write something like mailing list 1 dot merge mailing list 2, I know that in fact it's mailing list 1 that is going to be changed, and not mailing list 2. Okay, and the rest of this pretty much follows along the lines of that. Here I've got an internal helper function for removing a node from a mailing list. That removal can actually change the, well no, those are passed by copies, so that's okay. That will not change those pointers. All right, so that's const correctness. And that's the last item in our checklist. So, for the rest of this course, whenever you find yourself in a situation where you are responsible for designing a new abstract data type interface, you should think about these. Later in the semester, when we cover Java, we'll have a similar list for Java. This set of rules, this set of 12 rules, is very idiosyncratic to C++. Many of the same things will not apply in other programming languages, but it's good to provide a list like this for other programming languages. So when we get to Java, we'll take a look at those then. But do keep this checklist in mind. As I said at the beginning, these are not inviolable rules. You can sometimes say, I have decided to violate this particular rule because. But you should always do so consciously, having decided that you really want to make an exception to one of these rules, and you should always be able to state, at least to yourself, what the reason is for making that particular assertion. It shouldn't ever be simply because I didn't think of it.